Hi.
Hey guys, can you hear me?
Yes, yes.
Yeah.
Oh, cool.
Yes.
How is it going so far for the course?
Yeah, checking the videos in the platform. Try to
Oh,
do
okay.
that.
Yeah,
This,
actually, at the beginning, I think it was kind of hard, at least for me. Just in the last week, I had a better grade. um, but I think
Oh,
that
mhm.
it's a quite challenge in this course.
Oh, I see. So which challenge about which material, MLE or maybe some other material? Which
Uh,
part?
And I mean, I think it's because it's a little new the subjects, but for the materials, I don't know. I think it's okay. How about you, Joel?
I see.
yeah,
Yeah, so
for-
I think start from last week and this week we will move into the multivariate statistics. So maybe things will becomes a little bit complicated because we move to from one dimension to high dimensions. But I think yeah, the basic idea is you think the conclusions and the theory would be the same, but the only difference is you need to multiply from the variables to the matrix. You will,
okay.
I think you would need to review some of your linear algebra things, and I think there will be a separate called the prerequisite course teaching about linear algebra and calculus start from next month. So I think that would be help you to review some basic math to help you to learn better for the multivariate statistics. Did that help you?
Okay.
Yeah. So don't worry if you think currently the math is a little bit complicated. But I think the basic idea is you should formalize the problems and don't think too much about the math itself, right? Just think about how to solve these problems. So yeah, and I will explain you the intuition behind it. Yeah, I think the recitation is not like to just prove the math, but help you to obtain some intuition and tell you how do I memorize all these theorems and equations, right? Because I learned all this stuff 2 years ago. So I totally understand the challenge you faced. Okay.
Okay. Thank you.
Yeah, no problem. Yeah, I think we just wait 1 minute, another 1 minute, and we will get started. Yeah, so if anyone have any question for the course, you can just unmute yourself, okay, and interrupt me. It's okay. So we will just wait for another minute. Okay, I think we could start at this time. Okay, let's get started. So today's agenda is we will continue our the maximum likelihood as we talking about last week. So last week I just tell you how do you achieve the MLE conclusion from the KL divergence. So this part I omitted from the recitation because I think the professors explained very well in his lecture. So please see lecture from how do you derive the conclusion from minimize the KL divergence to the maximum the likelihood, okay? And we talking about how do you define the likelihood, how do you calculate the likelihood, and using some optimization techniques to get the results. And so this week we'll continue these topics and I will give you a concrete example, and we will do it together. Okay, so this is for the MLE. The second big part is actually we will move on to the multivariate statistics. So this part is including the covariance, which is a way to define the relationship between each dimension. Okay, we will need a matrix to help you to calculate the relationship that is we call the covariance. And the second is we will we will learn the multivariate Gaussian, right? So last time so at the beginning we learned the 1D one dimension Gaussian, but this time we will learn the multivariate Gaussian. I think you already learned from the lecture, and we will review the multivariate CLT and multivariate data methods. All this stuff you already learned in the previous lecture, but the only difference is it's from 1D to the multivariate dimension. Okay, so this is the overview of today's agenda. Okay, so let's get started. So for the maximum likelihood estimate, so we will review the definition again. So consider a data that is we call the sample, right? It's an IID sample from a statistical model or a distribution. Given the observed value xy to the xn for the data, okay? So the x1 to the xn is actually we call a data is a real value, okay? Is a real value. We call the data, and we plug in the data itself to the PDF, right? And then we multiply all this stuff, we will get the likelihood function. Okay, so the likelihood function is a real value function. We plug in the real world data to the PDF, and we will get the likelihood. Okay, you can think of the likelihood is like the probability. If the likelihood is high, means the probability you plug in is high. But actually, I told you the difference between the likelihood and the probability itself, right? They are similar because if you think about just the formula, but actually they are a little bit different. Okay, but you can think is that the likelihood is high. Maybe there is a more likely the thing would happen. Okay, this is more difference. So this function we call about the parameters we call the likelihood function. Okay, so the MLE is basically just optimize this function to get the optimal parameter, optimal theta here. So I think MLE is easy because you just sum. Okay, so this part we will place add a log at the front of the likelihood function. The basic idea is why we place a log, because if you just do the calculation, the multiplication is complicated, right? If we add a log at the front of the likelihood function, we will replace the multiplication to the summation. The summation would be very easy to manipulate, right? So in this case, we place a log, so it will become a log PDF, right? The log of the likelihood function. So this we will, so it would become a summation. Okay, so it would become a summation. Okay, so this is the basic idea of MLE. You just the sum of the log of a PDF, right? If you place a log, it would become just the log of the PDF, and calculate the gradient respect to your parameters, right? Because you calculate the gradient and just calculate the score function, right? So here we get the L theta, and we calculate the gradient respect to the theta and equal to 0, and calculate the optimal theta that maximize the likelihood, maximize the log likelihood. Okay, so I think every case in this case you optimize the log likelihood. Okay, so the log likelihood is just a the likelihood, because the solution would be the same, because we place a log because the summation is pretty much easier to manipulate. So that's it. Okay, so this is the definition of LME. So today I will go through a concrete example, okay, to help you to review the MLE, because I think this part is really important and would be both in your midterm exam and your final exam. Okay, so let's get a concrete example of calculate the MLE estimate of 1D normal distribution. Okay, so I will walk through these examples step by step. So for the 1D normal distribution, it would be we have two parameters. One is the mu, right? Is the mean. So another is the variance. We call the sigma square. Okay, this is the 1D distribution. So if we have some data, IID means identically independent distribution following the normal distribution. We have two parameters. How do you calculate the optimal, which means the MLE estimate of a mu, and the MLE estimate of the sigma square? Okay, that would be hat, means it's an estimate. Okay, and I place a star sign, means that is optimal value. Okay, so how do we do it? So first, let me write down the PDF. Okay, so everything you start from the MLE is just write down its PDF. So step one, write down the PDF. The PDF of the 1D Gaussian would be this one, right? As I write down on the left, I just write it again. Okay, so this is the PDF. Okay, so then we calculate the likelihood. Okay, first we write down the PDF, then we calculate the likelihood, or we call the log likelihood. Okay, the second step is calculate the log likelihood. But calculate the log likelihood means you just sum of the log of the PDF, right? That is, we just need to sum of the logarithm of the PDF, right? Based on the on our conclusion. So that would be, so the log likelihood function. Okay, this is the log likelihood function with the summation from 1 to the n of the log likelihood. That is the log of the PDF. Yeah, as I just write down at the left, right? This part, and then for the log, we will get this one, right? Because we just place a log inside, and then we will get this one. Okay. So, okay, I will do the math for you again. You place the log, right? And then you will get this one. And because there is an explanation, and you will cancel out, and you will get this one. And for this part, you just undo this part, okay? You will get this one. I think that would be, because you know this one, okay, this part would be the would be the same, right? Because 1 to the n, this one would be the constant, so you just place the n at the front, okay? Log sigma square, and this one we move the summation inside, okay? Yeah, if anyone have any problems, just unmute yourself and ask the question, okay? So then this is the we write down the log likelihood. The second step is is just do the calculus, okay? The calculus means you just calculate the gradient respect to the two parameters, right? Calculate the gradients and get the optimal value. The optimal value would be the estimate itself, okay? So as I write down in the left, so we will calculate the gradient, okay? Calculate the gradients. So for example, if we first calculate the gradient respect to the mu, right? So this don't have mu, so cancel out. This don't have a mu, cancel. So for this, we calculate the gradient respect to the mu. So that would be like the sigma, the constant. So well, that one to the 1/2 will cancel out to the gradient of this. Here we have a 2, right? So it cancel out. So that would be the summation of xi minus mu equals to 0. And then we calculate here from the mu, right? So this one for the mu, so we will get the mu. So just this one to be the mu, right? Because the sigma, the 1 over sigma square is a constant, and then we will have a it's just have a sigma 1 summation 1 from the n xi minus n mu, right, equals to 0, and we have a mu. The estimate would be the summation from the 1 to the n xi over n, right? So actually this is just a mean of our data, right? So here we already calculate the mean and calculate the estimate of mu. Then we plug in, right? We plug in to this function. We plug in back to this function and then calculate calculate the gradient respect to the sigma square, right? So then we as I said, I calculate the gradient respect to the sigma, okay? So that would be, yeah, as I write down at the right board. So that would be this one. If you calculate the gradient, right, respect to, that would be the gradient, the log likelihood, the gradient of log likelihood respect to the sigma square, okay? That would be this one, equal to 0, and you plug in the mu, right? Because now we will have the optimal mu, and now we will get the optimal sigma square. I don't calculate this time, but you can convince yourself that it would be that would be very easy to calculate. That is xi minus x bar to the square, okay? So the basic idea is if you have like 2 parameters at this time, okay? If you have 2 parameters at this time, for example, if you have a mu and sigma, so the first is just calculate 1 parameters first, okay? So if we have a mu to estimate, we have a sigma square to estimate, just estimate 1 parameters at first, and then as you plug in the results of this optimal value and calculate the second parameters. So I think basically the mu, the mean of the parameters would be easy to handle with. So first, I think at the so generally you first estimate the mu, and then you plug in the value of your optimal mu and calculate do the calculus, right, and calculate the estimate of the sigma square. So that is the basic idea. So, but there is a one thing to notice that is here. Okay, so if you are very familiar with this formula, right? This formula is actually when you calculate the variance of x, right? We calculate variance of x, we just summation from 1 to the n xi minus its mean, right? And divided by n. That is a variance. But I shouldn't say that actually this sigma square, the estimate of sigma square is biased. Okay, it's biased. It's what I mean bias. If it's unbiased means, if one estimate is unbiased means, for example, if mu is unbiased means the expectation of our estimation, right? This is our estimation, would be equal to the two parameters. Okay, but at this time, why I said the sigma square is biased, but the mu is unbiased. Okay, this is unbiased, but the sigma square estimate is biased. Why? Because that would means the sigma square, the expectation of your estimate would not equal the true sigma square. Okay, but why? You can prove yourself, convince yourself by calculate the expectation of the sigma square. Okay, and actually, what is the unbiased estimate? The unbiased estimate would actually be this one. You replace the y over 1 over n to the 1 over n minus 1, right? So that would be not n at this part. That would be the n minus 1. Everything would be the same. So this is the unbiased estimate, okay, of the sigma square. Yeah, if you calculate the expectation of this stuff, that would be equal to the sigma square. Okay, so this is the so you can think of this way. If you we will learn the linear regression, and the linear regression, we will talk about the degree of freedom. Yeah, you are not required to learn this at this time, but I just tell you that if we have n samples, and the degree of freedom would be n minus 1, right? It's not n this time. The degree of freedom is n minus 1 because we have a requirement that we already know the mean, the mean of x, right? So that would be cancel one degree of freedom. So the degree of freedom is n minus 1. So you would learn this, I think, in the following lecture, but here I just point out that the MLE estimate of sigma square is actually biased. Okay, so I think sometimes we require that the estimate is unbiased. Okay, but this times the MLE of the estimate, that is biased. So actually, I would say the MLE is all the only thing you should know, right? Because MLE also have some disadvantages. At this time, the MLE's estimate is biased. Okay. So this is, I should mention, for the MLE for the 1D normal distribution. So so for the bias or unbiased, you are not required to know at this time, but the only takeaway for these slides is you just need to memorize the how to calculate the MLE. Okay, the first step, write down the PDF. The second step, sum of the log of the PDF, and the third step is do the calculus, calculate the optimal value. So that's it. Okay, so this is for these slides for the MLE. Oops, sorry. So we will move on to the next slides. Oh, Okay, so so this week I will talk about some very nice properties of MLE, right? That is we say we call the constancy and asymptotic normality. So I think last week I told you that why we prefer to use the KL divergence rather than the total variance distance, because even though the total variance distance is a true distance, but we prefer the KL divergence because the KL divergence will derive the MLE, and MLE, the estimate will have very nice properties, okay? So we will talk about actually 3 properties, but the 2 of them are very important, okay? And as we talk in the teach in the lecture. So one is we call the consistency. The second is we call the asymptotic normality, okay? So first, let me review the definition. What is we call the consistency? The consistency is, so from the last slides, we talk about one we call the unbiased, right? Unbiased means the expectation of your estimate would equal to the true parameters, okay? This is we call the bias, the unbiased. But for the consistency, that means your estimate parameters would be convergence in probability in the true parameters as you increase your sample size as the n approach to the infinity. Okay, that means your parameters, your estimates will convergence in the true estimate. There are not like the expectation. Okay, just for the parameters converges in probability to your true parameters. That is we call the consistency. That means when you increase your sample size, okay, from maybe 100 to 1 million. So that means the parameters you estimate will approach to your convergence in probability to the true parameters, okay? This is the true parameters. This is the estimate. Okay, so this is we called the consistency. The second is the asymptotic normality. Asymptotic normality means this one convergence in distribution to a normal distribution, okay? The normal distribution that would be have some variance, okay? Some variance, okay? So here I don't write down the variance because the variance would have some different formula, but this is just some variance, okay? That convergence in a normal distribution. So actually this one is pretty much likely the CLT, right? If we remember the central limit theorem, we would have the CLT would be the square root of n times the parameters convergence in the standard deviation, right? If we divide it by sigma square, it would be convergence in the standard normal. Yeah, so this one is basically the same, right? You just place the sigma square here, right? That would be the same. But the basic idea is the CLT is we calculate the mean, right? This is actually the mean. Let me write down again. So that would be the mean convergence to the normal distribution sigma square, okay? So the CLT is a theory about the mean of X, right? But here the only difference is here we talk about the parameter, right? We talk about the true parameters and the estimate of the true parameters. But the basic idea is all they are convergence in distribution to a normal distribution, right? Here is a normal distribution. There is another norm distribution. So this is we call the asymptotic normality, okay? So this is the definition. So the consistency and asymptotic normality of the MLE actually generate hold for many parametric model, okay? So And there is a general formula for this asymptotic variance. So if we know, so when we know the CLT, we know, wow, it's very useful, right? Because if we care about its mean, we would write down the CLT, right? And the CLT will help us to get the estimate, define the confidence interval you will learn in the following lecture. Because we will learn the distribution of the mean, right? If we know the CLT, we will know the distribution of X bar, right? Because we know its convergence to a normal distribution. So then we would know its distribution now is pretty much easy to handle with because the normal distribution is easy, right? The same way, similarly, if we know that its conversion to a normal distribution, then we know the distribution of sigma, right? We know the sigma hat, right? The distribution of sigma hat. Then we can either define the test because we already know its distribution, right? Like a normal distribution, and we can get the estimate, right? We can do the statistics because we already know its distribution. So, but I would say that even though the MLE has these two nice properties, it has conditions, right? It should be under some mild regularizations conditions, and then the MLE would have these nice properties. I will show you in this slides. Okay. So this is actually the formal theory of the MLE estimate. Okay, but that would have some regularities condition, right? That is here. If we satisfied on these four conditions, that means the MLE would have the consistency and asymptotic normality, okay? If we satisfied all this stuff, that implies the MLE has both consistency and, oops, the second one is asymptotical normality. The two nice property, okay? So this is the basic idea of the theory, okay? But I should say don't remember this condition because this is you don't require to know actually, because in this course, I think both in your real life, I think all these conditions are hold itself. So you should not to memorize this stuff, right? Just the only thing you need to know is there is some requirement for you to have this conclusion, to have this theory. Okay, so if you wanted to apply this theory in this course, this condition already holds. Okay, but in some real life, in some very limited cases, this condition actually not hold. At that time, you should think about if the condition not hold, the MLE not have the consistency of asymptotic normality. These two properties not hold, doesn't hold. But for this course, you should already assume that all these conditions are actually hold. Okay, so this is the theory. Okay, so then the asymptotic normality means that we would have a very similar to the CLT, right? We will have this conclusion. That means we would convergence in distribution to a normal distribution, and the variance actually have a formal definition that would be this is the variance, right? But the variance is actually the 1 over its facial information. I would talk about what is the facial information means later, but this is the definition of asymptotic normality, right? it's hold for the asymptotic normality. And the nicer is there is a general formula for its asymptotic variance. Okay, so actually we have a closed form for the variance that is a 1 over of its feature information, and the feature information is defined this way. That is the variance of the variance of the z, right? The z function is actually we call the score function. Okay, z function is we call the score function. The variance of a score function is just equal to the minus of the derivative and the expectation of the z score times the -1. Okay, this I think this conclusion will be approved in the lecture, so I don't go through the details how to prove this theorem, but I think the basic idea, how do I memorize the feature information? Okay, the feature information is just a variance. Okay, so that should be the variance of something, and the something is here. We would calculate the log of the so this is the z score function is actually just calculate the gradient, the first derivative of the log likelihood. That's it. Okay, so I think the way to memorize this asymptotic variance. So first we talk about MLE has asymptotic normality. Okay, but have an asymptotic normality, you should calculate the variance. Okay, but this time we should say the theory told us the variance is actually the 1 over its feature information, but we should know about how to calculate the feature information. The feature information is you just calculate the score function, and then you get the feature information, get the variance, and we will write down the asymptotic normality. The score function is just the derivative, its log likelihood. Okay, so so I will write down this way. So when you do the homework and the final exam, so first I think let me use another color. So the step 1 is write down the log of your likelihood. Okay, the second step is calculate the score function. That is, we just calculate the first derivative of the log likelihood. That is the score function. Score function. And the third step is when we calculate the score function, right? That is equal to the z x and theta, right? And then we calculate its the second derivative, that is of the log likelihood, right? That is the second derivative. Okay, so this is a derivative of score function, but this is the second derivative of your log likelihood. Okay, so and the third step is calculate the expectation, the minus expectation, okay, of the second derivative you calculate. So this is the derivative of a score function, but this is the second derivative of the log likelihood. Okay, you calculate this, that is equal to the feature information. And the third step is to write down the asymptotic normality. That is, that should be convergence in distribution in a normal distribution. The mu is the 0, and the variance that should be 1 over 1 over the feature information. Okay, so this is so this is the 5-step you calculate the problems. Okay, so I think the basic idea is get the log likelihood and then calculate twice. Okay, do the calculus twice. The first, the second step is get the score function, but you should get the derivative, the second derivative, and get the derivative of the the score function, and then calculate the minus expectation of it, and get the feature. This is we call the asymptotic variance. When we get the asymptotic variance, we can write down the CLT-like formula, right? When we get the CLT-like formula, that is equal to, say, theta is follow this distribution. Okay, this is the same because you just plate the sigma square to the mean, right? That is here, and then you divide it by the n square, right? The both divided by the sigma square, and when you place in the variance, you should the square root of them, right? That would be the m here. So actually, we already know the distribution of sigma square, right? That means we know the distribution of our parameters. And then we can do any test you like based on the theta, right? Because at this time already know its distribution. So it's very easy to conduct any test you like, right? So why we think the MLE is very crucial in this course, because MLE can write down the asymptotic normality, right? Because we like asymptotic. Why? Because asymptotic means that when your sample size gets bigger, it's approach to a normal distribution. We think normal distribution is very easy to manipulate, right? So as I said from the I think the first week recitation, so that should be any parametric model, right? The fx can be any models, like the exponential distribution, like the beta distribution, like the gamma distribution, or any distribution you like. But when we calculate this stuff, the asymptotic normality properties tell you that it should be converges to a normal distribution, right? If this formula, this stuff converges to a normal distribution, that means equivalently, your parameters will follow this normal distribution, okay? If we already know the parameters follow a normal distribution, then we know its value, right? Because we already know at any times its distribution, we know how to conduct the test because we already know its distribution. I think for a random variable, if we already know its distribution, its PDF, we know everything, okay? So then we know everything for the parameters, then we can conduct any test upon it, okay? So this is the basic idea. So the both CLT and asymptotic normalities tell you that we can converge any fancy distribution to the normal distribution, okay? This is the nice property of asymptotic normality. But please notice that this is called asymptotic, means the n is approached to infinity. Okay, if you only have 5 or 10 samples, you cannot use this this conclusion, both for the CLT and asymptotic normality doesn't hold. But what is the CLT? What is the difference between the CLT and the asymptotic normality, right? I think maybe some students are confused about it. What is the difference between the CLT and the asymptotic normality? So as I said in the previous slides, both formula is just the same, right? But the CLT is the function here, the function of the X bar, okay? But the asymptotic normality here is not X bar, it's not the mean of our data, it's the parameters we wanted to calculate, okay? And for the CLT, we actually converges to a normal distribution, right? The sigma square is the true parameters, but for the asymptotic normality, this is asymptotic normality. We have a very nice form for the variance. That is, we don't need to. We have something to calculate the variance. Okay, we already know the variance. The variance is just 1 over its facial information. That is very nice because the only thing is I just need to write down the log likelihood and do the calculus, and then we will calculate the feature information. We don't need to like do very complicated math to get the variance, okay? Because sometimes calculate the true variance is very difficult, okay? But at this step, the theory told us the variance it has a closed form that is 1 over its feature information, okay? And the feature how to get the feature information? The feature information is your calculate the second derivative of the log likelihood, okay? The score function is calculate the first derivative, and you calculate derivative again, that is the second derivative. You get this, and you just calculate its minus expectation, and then you will get the asymptotic. You will get the asymptotic variance, okay? So that is the basic idea. I think when I first learned this theory, somehow it could be a little bit complicated. But I think the basic idea, how do I memorize this theory, is start from the log likelihood, okay? As I write down in the green pen, right? First calculate the log likelihood, and then do the calculus and get the asymptotic variance and write down the formula. And then, as I write down here, okay, we would get the distribution of our parameters that would be following following a normal distribution with some variance, and its variance is equal to the 1 over its visual information, okay? Okay, but I know some students would say why. I think it's also confused to me when I first learned this theory. Okay, I should say why it converges to a normal distribution. Okay, so I don't show a proof here, but just give you some basic idea, and you can Google for the concrete proof. Okay, here I just give you a sketch of the proof. So first, for a consistency, why MLE has consistency and asymptotic normality, right? This is the question. So first, how do you prove the MLE is consistent? Just using the Jason's inequality, okay? Actually, this proof is not too much complicated, okay? You can just Google online, and I will show you the a reading if you are interested. But actually, in the real world, or for this course, I don't think you should to memorize that proof. Okay, you just know about the conclusion. Okay, the basic idea is just using the Jason inequality and to calculate the expectation, and using the Jason inequality, and you will get the results. This is for the consistency. For the asymptotic normality, we first prove the probabilities of the score function, that is here. And then we applied the law of large numbers and the CLT and the Slutsky lemma. These three are the Slutsky lemma. I think I don't know if Jeffrey tell you about this theory. I think this theory is very important in the probability course. Okay, so if you don't remember and Jeffrey doesn't tell you go review of this lemma, please review your probability course. Okay, and then here we will using the Slutsky lemma to prove that this. Sorry, actually this one is a convergence in convergence in distribution of a normal distribution, and its variance is just its feature information. Yes, this way, right? When you apply the Slutsky lemma, okay, this is not a proof. It's just like to show you some idea of how you prove the consistency and the asymptotic normality, because I don't like just waste another half of hour to formally prove it. But actually for this course, just memorize the conclusion, right? It's very easy. It's just like the CLT, right? There is a consistency and the asymptotic normality. Okay. So this slides we show the asymptotic normality, right? And the consistency is very easy. The consistency is just like the MLE of our estimate is convergence in probability of the two parameters as n is approached to infinity. That is the consistency, and this is the asymptotic normality. This is consistency. This is asymptotic normality. Okay. I know this stuff is a little bit complicated. So if anyone have any questions, so please unmute yourself and asking question or type in the chat box. Okay. Does anyone have any question or confuse the point for the MLE estimate? Oh, this is the MLE estimate. Okay. Have a nice property. Yeah. If you guys have any questions, so feel free to asking the question. Okay, so great. Let me move to the next part. The MLE is crucial in our class because you will apply it so many times, right? So in some sample cases, if we just care about the mean of X, we just apply the CLT. But when we wanted to calculate something more complicated, we will apply the asymptotic normality or the delta method. And furthermore, we will apply the delta method upon it, right? Because the delta method says if your theta has some asymptotic normality, and if you wanted to have, if you are interested in g of x, right, you will apply the delta method. So this is just like the way you should approach to get the distribution of your parameters. Okay, so that would say this is just the takeaway, right? How do I memorize this theory? Is if we want to get the distribution of parameters we interest. First, think about the CLT. If the parameters we are interested is just the x bar of x, then we just apply the CLT, right? Because the CLT is about the x bar, okay? That means if the distribution, if the parameters we interest is just the mean of x, then we calculate the CLT. If not, then, but if not the mean of x, but it's a MLE estimate, then we will apply the MLE asymptotic normality. I will give you an example. Okay, I will give you an example. And the third is furthermore, if theta itself is asymptotic normal, but we care about the g of theta, right? For example, the log of theta, the theta square, right? But we care about the g of theta. Further applied the delta method. Okay, that is a basic idea. If you wanted to get the distribution parameter, why we wanted to get the distribution of the parameters? Because we want to calculate the true mean, its true variance. We wanted to calculate the confidence interval when we do the test, right? You will learn all this stuff in the following weeks. So okay, so then I will just give you a exercise that is verify the theory is correct for the Poisson examples. So for the Poisson examples, the PDF is we could write down this way. Okay, so this exercise is just to convince you that the theory is correct. How do you get that? How do you verify the theory is correct? So when you, so I will give you a hint. So just apply the asymptotical normality, right? You first calculate its feature information, right? You calculate its feature information here, and you write down the asymptotic normality. That is the same as you use CLT, okay? Because why we can use the CLT? Because the lambda of the Poisson distribution is actually the mean, okay? Because the EX is equal to the lambda. So that means when we try to estimate the lambda, we can use we can use the mean of the data, right? That is the X bar, right? If we can use the X bar to estimate the lambda, we can just write down the CLT. Okay, we can just write down the CLT. But another way to do it is using the asymptotic normality. Okay, you can obtain the same conclusion. So this just give you a hint to say how to verify that this asymptotic normality theory is correct. So here I just will send you to the breakout Zooms, and either you could help you to review the CLT, right? Just write down the CLT and to say if you applied the asymptotic normality, calculate the asymptotic variance, that will convince you that you use a two-way and you will get the same conclusion, and we will work this example together. Okay, so let me just send you to the breakout Zooms, and you will discuss how do you calculate the feature information. Okay, the feature information is very easy, just using the step here. Okay, just calculate the log likelihood. Okay, so then I will send you to the breakout Zoom. This is the second exercise today. And I will give you like maybe 8 minutes, okay? 8 or 10 minutes. So now I will send you to the breakout Zoom. Okay, so cool. So does anyone get the everyone get the answer correct? Help to verify the this MLE theory. So I will show you both from the CLT. Okay, I will show you both from the CLT and both using the MLE to achieve to get the same conclusion. Okay, so first let me do the CLT side. So first, for a Poisson distribution, we know that its variance equal to its expectation equals to lambda. Okay, this is, I think this is a very common conclusion. You should to memorize. Okay, it's because it's used so many times. So because we know the lambda is equal to its expectation of x, right? Means we can estimate the lambda using the x bar. Okay, cool. If here we wanted to estimate the parameters is equal to the x bar, means we can just apply the CLT. Okay, so the CLT means the x bar minus its two parameters is converges to the distribution of a normal distribution, that is the variance. Okay, the variance, but its variance is just equal to the lambda. Okay, so this is our final conclusion. Okay, because its variance is equal to the lambda itself already. Okay, so this is just apply the CLT, and we know that if the parameters we are interested is equal to the x bar, we can just apply the CLT, and CLT is very easy. Okay, so now we can apply the MLE. Okay, so first let me write down the log likelihood. Okay, the log likelihood would be the log fx lambda. That would be the log of this stuff, right? So that, let me write down this way, and that could be the x log lambda minus lambda log the log of factorial of x. Okay, and first we calculate the score function, this first derivative. Okay, that would be log of this one. That would be the calculate the gradient. That would be this one minus 1, right? Calculate the derivative, that would be this one. And then we calculate the second derivative of the log likelihood, that is the derivative of a score function. Okay, that could be the derivative of this stuff, that could be x to the lambda, that would be the x over the lambda square. Okay, so then we calculate the Fisher information. Okay, we know about the Fisher information is equal to the minus, please note that there is a minus of the second derivative of the log likelihood, right? That is just the minus expectation of this one. Okay, that should be the okay, so because we know the x is already the lambda, right? So that would be the ex is lambda, so that is the minus cancel out, so that could be 1 over lambda. Okay, and then we apply the asymptotic normality. That means the asymptotic normality tells you that the square of root of then and the lambda of the MLE we estimate minus the true lambda we get is convergence in distribution of normal distribution, that is n, and the variance, now we have a closed form, right? For the CLT, we don't know the variance, we need to calculate, but for the CLT, we know that it should be the 1 over the Fisher information. Okay, so if you place the n square to here, that would be 1 over n times the Fisher information, but you replace the n here, that should be no n here, right? So that is equal to that is equivalent to the n the mean is 0, and the feature information is 1 over lambda, that is lambda. Okay, so now, well, it's fantastic, right? For the CLT, we get this conclusion. For the asymptotic normality of MLE, we get the same answer. Okay, so I think today's exercise do help you to understand how to calculate the MLE and convince you that the MLE theory is correct, right? So why do we care about the MLE of lambda? Okay, this is actually the concrete example to help you, right? So if we don't know its expectation and variance equal to lambda, but we can calculate the MLE estimate of a lambda, right? If we give you a fancy example, just calculate the MLE and using the asymptotic normality, and you will get the answer, right? Because sometimes applying the CLT is could be difficult, and some case we cannot apply the CLT because the CLT is a function of X bar. If the parameters you are interested in is not related to the X bar, you cannot apply the directly apply the CLT. You may apply the CLT plus the delta method, okay? Or something you apply the asymptotic normality plus the delta method. The delta method is as I showed you here. If we know the theta is asymptotic normality, but we care about the g of theta, the function of theta, we will apply the delta method, okay? So here is about the feature information, but I think we already go through the detail of it, right? This is the log likelihood. We calculate the first derivative and then calculate the second derivative. And this one is the score function, okay? This is actually the derivative of score function. And here the feature information is equal to the minus expectation of the derivative of score function, okay? So, but more generally, this is a one parameters parametric model, like the Poisson distribution. We only have a one parameters, okay? But if we like beta distribution, normal distribution, we have a 2 or 3 or 4 parameters, okay? But how do you get the feature information? That would be change to the feature information. That would be, this is a value, okay? Change the value to a matrix, okay? This we call the feature information matrix. This is a more general form. So just replace this one to this one, right? Because this one you calculate the theta twice, but this one, this is a matrix. Oh, sorry. This is a matrix, means this is a k-dimensional, this is k-dimensional when we have a k parameters, right? When you calculate the derivative, that should be derivative. It's pretty much like the Hessian matrix, right? Calculate for the sigma 1 and sigma 1, right? That is just like here, right? But the second is first calculate derivative respect to theta 1, and then we calculate derivative of sigma 2, right? And this part is calculate first derivative respect to the theta 1, and then theta 2, right? And then calculate the gradient respect to the theta 1. Okay, this is like the k to the k matrix. And then that is the same, right? For a value converges to the 1 over the value, right? But here for the matrix, you just calculate the inverse of matrix. Okay, so I think for this course, the most complicated problems you will meet is just like the normal distribution or beta distribution is have a 2 parameters. For this course, you are not required to learn about like more than 2 parameters, okay? If you have only 2 parameters, so for example, if you have only 2 parameters, so the matrix would be log of the probability respect to the, if we have a parametric model like the fx theta 1, theta 2, right? That is theta 1, theta 1, theta 2, theta 2. Okay, this is the theta 1, theta 2. This is the theta 2, theta 1, right? Just calculate the matrix and calculate the inverse of the matrix, right? Calculate the inverse matrix is not like just the 1 over it, okay? This is not equivalent to the 1 over all this stuff, okay? Calculate the inverse matrix, please revert your linear algebra course. And actually we don't do in the real life calculate by hand, right? We just use the software to calculate. So this is just a more general form of the Fisher information matrix, okay? So more about MLE. I think I don't remember if professors know that this slide in the lecture, but this is very important. I want to notify you is the MLE have a lot of very nice properties. Not only for the consistency, asymptotic normality, what's more, we call it the asymptotic efficiency. That is, it have a lowest variance. It has lowest variance, right? We know if we calculate the variance is, if we calculate the estimate, we have a bigger variance, means the variation is big, right? But if we calculate the same variance, the same estimate, but with little small variance, means we are pretty much confident that they are fall in this region, right? So it have lowest variance means that there are no variation, right? So that means it pretty much fall in this region. We are more confident. You can think about this way, okay? So this lower variance we call the primary route lower bound, okay? The CRLB, the primary route lower bound. But you are not required for this course. This is just help you to understand why we use the MLE, because MLE have a lot of very nice property. It's consistent, it's asymptotic normal, and also its variance is the lowest, right? Any unbiased estimate of theta based on the data, the variance you calculate is pretty much bigger than the asymptotic normality variance. Okay, this is the asymptotic variance, okay, as we get the Fisher information, right? This is the variance of MLE. MLE's variance. Any unbiased estimate the variance would be greater or equal than the MLE variance. So the MLE variance is very efficient. We call it the asymptotically efficiency, because the variance is lowest. So sometimes we have a different methods of estimate, right? We have methods of moments, right? We will learn in the following lecture. We have a MLE, right? We have or other way of estimate, right? But the MLE achieve the lowest variance. So generally, if we have a different methods to get the estimate, so the first choice would be the MLE, because the MLE you get is have a lowest variance, okay? But the second things I would to notice that the MLE is not everything, right? It's not the only thing you should know, because in some cases, there is a no closed form expressions for the estimate, okay? For example, when we do if we apply the MLE for the gamma distribution, there is no closed form for the alpha, means you cannot get the MLE estimate, closed form estimate of the alpha of the A in the gamma distribution. Okay, so sometimes there is impossible to apply the MLE directly. So you also need to learn other way of estimate, like the methods of moments of other ways. Okay, so MLE do have its disadvantages. And I also noticed that for the Gaussian distribution, right? Like I said, Gaussian distribution mu and sigma square, the estimate of sigma square is biased, is actually biased. Okay, so MLE do have its disadvantages. even though it have a lot of nice properties. Okay, that is you should take away for today's recitation. Okay, so now we move on to the second part. So the first part is continue about the MLE. The second part is maybe we don't have a lot of time today, but I wanted to show you that our course is move on to the next part, which is called the multivariate statistics, right? In the real world, when you handle the data, when you handle the parametrics models, the statistics model, I think the most of cases you have like the 2 parameters or even more, right? Because the Gaussian itself have 2 parameters. So we will extend the CLT from the 1-dimensional to the 2-dimensional, or even 3, or even multivariate statistics, right? But I think no worry, right? Because you just need to know the intuition behind the 1D statistics theory. The multivariate statistics is just a generation, okay? You calculate, so for the 1-dimensional CLT, you get the value, okay? It's a real number, but like I said, for the feature information, right? Just give you an example for the feature information. For the 1D, we get the value, right? But for multivariate things, you get the matrix, right? It's actually a K by K matrix if you have a K parameters, right? All this stuff, if for the multivariate statistics, you just multiply the matrix, not the values. That is for the multivariate statistics. Very easy, actually. I don't think you need to separately understand the multivariate statistics and the 1-dimensional thing. This multivariate statistics is just a generation of a 1D statistics, okay? So so let me review something you learned from the lecture. Okay, this is just I copy from your lecture. So so this is just we go for a review. The first is covariance. If we talk about multivariate statistics, the first thing I come to my mind is covariance. Why? Because we have a lot of dimension. We need to use a way to describe the relationship between each variable. We call each dimension, right? For example, if we have a X, Y, or 3 dimensions, X, Y, Z, right? We need to use some covariance. If a data point like this, we need to use some way to describe the relationship between X and Y, Y and Z, Z and X. So the matrix we use here is we call the covariance, right? We know the variance. The variance describe the variation along one axis, right? The variation is of X is equal to the right the EX minus EX times the X minus EX, right? Because this is just a square, right? You can also write down this way. Square. Okay, so but for the covariance, that you just place one X to the Y, right? That is the covariance of X, Y, and these have a nice property, right? So they are symmetrics. The covariance of X, Y is equal to the covariance Y of X, and when X, Y are independent, its covariance is equal to 0. Okay, this is some nice property of the covariance. Okay, but one thing to notice that I think the professors told in the lecture, the converse is not true, right? If the covariance is equal to 0, which only means that they are linearly something we call the linear independence, but actually they can be dependent. Okay, so the converse is false. Okay, so then we talk about the multivariate Gaussian. Right, this is we taught in the lecture. So here we just replace for the 1D. Let me write down this way. For the 1D Gaussian, we have its mu and sigma square. It's a value, right? The parameters is a value. But for the ND, we call the multivariate Gaussian. The mu is actually a vector, okay? The mu is a vector. And the sigma square is actually a matrix. Okay, it's a matrix. All these stuff are the same, right? If you write down the 1D part. Okay, that is basically the same, right? You just replace replace the values to the matrix. Okay, but one thing I need to notice is that for a bivariate Gaussian, okay, this is our graph. A graph shows the 2D Gaussians. We also call the bivariate Gaussian. Bivariate Gaussian, because we cannot show you upon the 3D, right? This is just a 2D Gaussian. So for the 2D Gaussians, please notice for the sigma. The sigma means the covariance matrix, okay? This is, so I just give you an example. This will be called the covariance matrix, okay? So if the covariance matrix, it means that the covariance of X and Y are 0, right? So there is a pretty much a bell shape, right? It's not like ellipse, right? Eclipse. But if we have something of along the diagonal, which means because for the 2D dimensions, there are covariance of XX, right? That is variance of XX, or variance of X, covariance of XY. Oops. Let me write down this way. For the bivariate Gaussian, the sigma square is the variance of X, covariance of XY, covariance of YX, variance of Y. Okay, so if we have along the diagonal, which means the covariance is not equal, right? That would the bell shape, right? The bell shape would behavior as an eclipse, right? It's not like a perfect bell shape. Okay, and you can see this figure. So it's look like an eclipse, but if the covariance are bigger, which means that the XY are highly dependent, right? The bell shape is more like behavior tight, right? So this is just a basic graph to show you what is how to visualize the covariance between the X and the Y. Okay, this is for the multivariate Gaussian. Okay, does anyone have any question? Okay, great. So for the multivariate Gaussian is just replace the value to a vector and a matrix that is, right? And then you do the algebra. Okay, then we will review the multivariate CLT. Okay, the multivariate CLT is actually is very easy, right? You just replace the mu to a vector, right? And replace the sigma square to the matrix, right? That's it. That is for the multivariate CLT. And for the multivariate delta method, okay? So for the 1D delta method, we have is for example here, right? The Tn is an asymptotic normality, right? And we care about the G of T, right? The Tn is asymptotic normality, which means that it has its convergence in probability to a normal distribution, and we care about the GT, right? For the 1D delta method, that is the GTn minus GT converges in distribution, that is G theta, the derivative to the right square, to the sigma square, right? This is the 1D, but here, this is the matrix, right? We replace the value to a matrix. That is the gradient of GT. The gradient is actually, you calculate, as I show you in the slides, that is the gradient respect to the first derivative, first dimension and the second dimension and so on, okay? So this is called the GT, the gradient. And the gradient, because this is a matrix, right? You cannot like write down the same way as a value, but this is a more general form of the multivariate delta method, right? All this stuff is the same. Sigma square replaced to the matrix, and the derivatives replaced to the gradients. So that's it. That is the multivariate delta methods, okay? But please notice that if you wanted to apply the delta method, this is a condition you should meet, right? This conditions means that the Tn is a asymptotic normality. Then you get a different expressions of the G of T, right? If Tn is asymptotic normality and you care about the G of T, the G of T could be anything, right? Like the 1 over Tn or Tn square or log of Tn, right? You can write down the new formula, right? But the G would be the function of the Tn, okay? But the first you apply the delta method, you should make sure that the Tn is asymptotic normality, okay? That's both for 1D and multivariate statistics, that we should satisfy this is the condition. Okay, if the condition is not, you cannot just like write down this way, because the Tn is not asymptotic normality. The GTn is the GTn is not asymptotic normality as well, right? Okay, so this is for the delta methods, and we will do the third exercise. Okay, so then I will again send you to the breakout Zoom, and hope you could solve these problems with your peer, right? So these problems is related to the multivariate Gaussian, okay? And hope you can get the solution, okay? I don't think I need to give you some big hint of it, because I think this problem is not complicated, okay? So just talking with your peer and get the answer. So now I will send you to the breakout Zooms, and I will give you like 8 minutes for this question. Okay, cool. Great. Welcome back, everyone. So hope you get the on the right track and get the right answer. So I will go through this question step by step. Okay. So for I don't think this question is very difficult. And this question is just help you to gain some intuition behind the bivariate Gaussian. Okay. So okay, so let's us go through this question together. So this is that if x and y are IID from a standard normal, and there are a parameters called rho, right? The rho is actually, you will learn, this is something called the covariance coefficient. Yes, you will learn this concepts when we dive into the regressions. But now you are not responsible to learn this concept. Okay, the rho is just a factor, and then we ask you if we have a linear combination of x and y. Okay, the rho is a real number. Okay, it's just a number, and the combination of a rho x and the combination of a y, what is distribution of x? Okay, so actually I don't expect you to approve this theory. Okay, but I just wanted to show you that the combination, there is a conclusion called the combination of Gaussian is also a Gaussian. Okay, this is just a combination, right? This is a ax and this is a y, this is a by, right? This is a combination of two Gaussian, x and y. X and y is a Gaussian, so z is actually a Gaussian. So z is a Gaussian. Okay, so because we don't have a run out of time, so I don't approve this concept, but just remember that any combination of a Gaussian is a Gaussian. Okay, so this is a Gaussian, but how? So it's not, right? We need to calculate the mean and its variance. Okay, so for the mean, let's calculate first. Okay, the mean is zx and the square root of b minus rho square y, right? We use the linearity of expectation and we move the expectation inside. So that could be rho times ex plus 1 minus rho square ey, right? Because we know ex and ey is both 0, right? So the ex would be 0. And calculates the variance of z, right? That is the same. But because we know the x and the y is independent, so we can just move inside. So that would be rho x plus 1 rho square var y, right? Because if the x and the y are not independent, so that, because here we know it's independent, is IID, right? But x and y is not independent, we should plus some covariance here, but x and y are independent, so we don't do this stuff, right? So the variance of x is a rho times 1, right? And the 1 minus rho square times 1, so it's equals to 1. So actually it's a standard normal distribution. Okay, this is for the question A. For question B, I write down here. For the this is for question A. For question B, so let me first calculate the covariance of x and y. Okay, covariance and x, y is equal to 0. Why? Because we know x and y are independent. Okay, so independence means covariance is equal to 0. But as I said, the converse is not true, right? But this way is true. Okay, x, y is independent, and its covariance is equal to 1. But how do you calculate the covariance of x and z? Okay, this one is a little bit tricky. But we can also use the definition. Okay, from the definition, we know we can write down in this way. Okay, so that could be, just use the definition. So that could be the E times the EX, right? Times Z times EZ. Okay, so that should be should becomes the because we know the EX is 0, right? The Z is 0, so that could be just the X times Z, right? And we place the Z inside, that is the rho X plus 1 minus rho square Y, right? And we just use the linearity of expectation, so that could be the expectation of a rho X, right? Plus the 1 minus square X and Y. So that could be the rho times EX plus 1, this one times EXY. Okay, so I write down this way. So because we know the variance is equal to the EX bar minus EX square is equal to 1, right? So so actually and we know this one is I don't think we need to use this. Okay, this is a square. Okay, sorry, because x times x is a square. Okay, so that makes sense. So the x square. So the EX square is 1 plus EX square. That is 1, right? So this one is 1. And what about the EX? The EX, because the covariance x and y is equal to the EXY minus EXEY, right? This one is equal to 0. Okay, is equal to 0. Also, this is not rho square. So sorry, this is a little bit mathy. So I write down again. Okay, so that would be the rho times EX square. Here we calculate is 1, right? And 1 minus rho square root, and times EX and the Y. And EXY is equal to 0 because this is 0, this 0, and the EXY is 0. Okay, so this is 0, cancel out. This is equal to 1. So actually, finally, the covariance of x and z is equal to rho. Okay, is equal to rho. So this is rho. This is the final solution for this question. So I think this problem is just multiply when multiplicates the variance and expectation. Okay, all this stuff is this. But the two takeaway is, first, the linear combination of a Gaussian is a Gaussian, and the second takeaway is when x and y and independent, so the covariance of x and y equal to 0. Okay, so that is this problems, and I think we don't have a time to do the third exercise. This is exercise related to the delta method, and we will move this exercise to the next week recitation. Okay, so I think that's all for today's recitation. I think we talk about two parts. The first part is MLE, continue from our last week stuff, right? We talk about lots of very nice properties, consistency and asymptotic normality and asymptotic efficiency, right? So we prefer to use the MLE. And the second big part is we call the multivariate statistics. We call the covariance, multivariate Gaussian, multivariate CLT, multivariate delta masters. All stuff can move from 1D to the multivariate stuff. But I think the only difference is you place the value, a real value to a matrix, and then you will do the linear algebra things. I think for the exam and for the homework, the most likely do is for the 2D, right? I think we don't require you to more than 2D. Okay, you just do the algebra to manipulate the matrix. So that's it, I think, for today's session. And if you have any question, I will leave like another few minutes. So feel free to ask me now. Yeah, if you have any question or any advice for the suggestion for the recitation, or you feel like you wanted to learn more things in next recitation, or wanted to help you out, so please unmute yourself and ask me question. Okay. So if not, like feel free to go. Okay, this is all for today's lecture. Okay. Have a good night, everyone. So if you have any question, just stay and ask me question. Okay.
Thanks. Have a nice weekend.
Have a good night. Yeah. Does anyone have a question? If not, just feel free to go. Okay.
Thank you. Have a good weekend.
Bye bye, David. Okay.
Thank you.
Okay, thank you so much. Have a nice weekend.
Estás en mute, Fiji.